Welcome back everyone to the Hello World Guide. This is another episode of the OpenGL tutorial series, and in this video we are going to get started using OpenGL to actually render stuff to the screen. So if you remember, in the last video we used GLFW to set up a window, and we used glue as well, and then we have got the clear screen working, and in this video we are going to learn how to use OpenGL and how it works and how to use it to draw different things on the screen. So let's go ahead and get started by first looking at what we had in the last video. So if you remember, in the last video we had this creation stuff for the window, and then we had the initialization of glue, and then we did this gl clear color command, and we are going to look more into how this all works in this video. And we've got, of course, our main loop, as well as in the end we just destroy everything. So if I go ahead and actually make that, you can see that we get a yellow screen like we should. Now let's understand how this works. So if you can see, we have got this command called gl clear color, and when I go ahead and run that, I just specify the color here, and then we only do that actually once, and then inside of the main loop we go ahead and do gl clear with gl color buffer bit. Now let's understand how this works. To understand this, let's first understand the model of OpenGL, how OpenGL is structured. So OpenGL is basically structured like a state machine, which means it has a bunch of it's a state machine in the sense that it has a bunch of different states and variables inside of it, and then we can use different commands to set them. And then we can, when we for example do gl clear and we want to clear the color, it uses whatever internal value of the color that should be used for clearing, it has got stored, and clears with that value, and that value is set by gl clear color. So when we call gl clear color, it actually sets an internal variable of OpenGL, you could say, and of course the details of this are implementation specific, but for a conceptual model we can say, for example, that it sets some sort of variable inside of OpenGL state machine, which sets that whenever you want to clear the color, you should use this color that is specified, and this color will be used until we call gl clear color again and we change it. So if we do it once and we don't actually change it, then this will be the color used every time. So in here you can see, when we in the main loop we use gl clear. This is the command that actually does something, and it tells it to clear the current frame buffer, and of course what all of that stuff we'll of course understand later. But you can see that currently, because we are not using anything specific, it just clears the screen. And this mask parameter that it takes, it basically is like a bitwise mask of different values, which tells it what kind of stuff it needs to clear. So we have got gl color buffer bit, and we have got gl depth buffer bit, as well as stencil buffer bit. Now what depth and stencil are, we'll understand those later, but for the color buffer bit, it basically specifies that it wants to clear the color of the screen. So when we ask it to clear the color of the screen, what it does is that it takes the gl clear color value that was stored, and it uses that to clear the screen. Now with modern OpenGL we have some things like direct state access, which makes the state machine model less pronounced. Like, you don't have to, for example, bind a buffer to do anything. We'll see that in a second. But fundamentally OpenGL is still a state machine, and that model isn't exactly how real GPUs work. It's a bit detached from reality, but it does work for more simple tasks. So now we have got our screen clearing, and we understand how all this works. We actually want to draw something to the screen. In all OpenGL you'd use gl begin and stuff, and you could specify the vertices of the shape you wanted to draw, and that was the fixed function pipeline. Modern OpenGL does not have that, and we are going to go ahead and do it the proper way, using the pipeline, or using the programmable shader pipeline that modern OpenGL has. So the way it works is that we can basically for example, if we want to render something to the screen, we can go ahead and render it as a bunch of points or vertices, or basically the data in this vertices is up to us to decide. So we can decide what sort of things each vertex has, and what it means, and then we can write our own shaders, and shaders are programs that execute on the GPU to basically transform or change those vertices. And of course when those vertices are rasterized, which means that they are, for example, used to create a filled shape, and of course there are different kinds of things we can do with the vertices. We can create triangles, we can create lines. We'll see all of those in the future, and then we can write another shader to specify how we want the coloring and the shading in them to be. And of course we'll understand how shaders and everything work and the pipeline works in the next video. In this video we are going to be mainly concerned with getting the basic stuff of writing having the vertex data basically, and specifying how the vertex data should be interpreted to OpenGL. So we are going to get started by creating, for example, some buffers. Buffers are basically a memory storage area for the for different types of data. Vertex data, currently we are only going to create one, and then we are going to specify to OpenGL how this data is supposed to be interpreted in this video. So yeah, let's get started with that. So the first thing we need to get started with is actually creating the vertex data. So in order to create the vertex data, we kind of need to know what space or what coordinate system OpenGL operates in. So OpenGL basically uses the normalized device coordinate system, and what this means is that regardless of the size of your screen, the left corner of the screen is at -1, the right is at +1, top is at +1, and bottom is at -1. And there's also the z-axis, but we don't need to worry about that right now. So this is basically the normalized device coordinate, and of course we can change this using different sort of matrices, and we'll see those in the future videos. But for now we are going to specify our whatever shape we want, and we are going to start by drawing a triangle. So in OpenGL, different types of shapes we can draw, which includes lines, points, and triangles, and some other things like line strips, etc. Those are basically variations of these three. And basically, in order to make more complex shapes, you have to basically use a triangle, many triangles, and you need to make the more complex shape out of those triangles. So you cannot, for example, ask the GPU to render a polygon. That is not how it works. You need to specify the polygon as different triangles, and then you need to give each of the triangle to the GPU, and it will render that. In old OpenGL, it was allowed to use GL polygon to draw polygons, but that didn't actually work that well, and of course internally it was still converting it to triangles, because GPUs are not able to draw polygons directly, they draw triangles usually. So yeah, let's go ahead and get started by defining the vertex data for a single triangle. So for this, I'm going to basically define the vertex data as an array of floats. So we are going to say vertex data, and we can go ahead and say it like that. And yeah, you can see that we have got this array here, and we need to specify the vertex data in here. And we basically want to use different sorts of basically we want to currently only specify the position for our vertices. So our triangle will have 3 vertices, and we need to specify the position for all of them. Currently, let's just keep it simple and 2D, and let's specify it in 2 dimensions. So for that, we are going to start by specifying the top vertex, which is going to have 0 and 0.5. So the total height of the screen is at 1. I'm going to set it at 0.5, and this is the top vertex. So you can see that the x value of this is 0, which means it's in the center, and the y is at 0.5, which means it's at the top. Similarly, for the bottom left, we are going to specify -0.5 for the x, and then 0 for the, actually -0.5 for the y as well. That will be our bottom left. And similarly for the bottom right, but this time we'll use 0.5 as positive on the x. And this will basically create an array of 6 floats, where each pair of floats represent the position of a vertex. So this is the vertex data. Now of course we can add a lot of different properties to the vertex data, and OpenGL by default has no way of knowing how this works. So in order to do that, we are going to use something called a vertex array object, or a VAO. So the way a VAO works is that it basically specifies to OpenGL the different attributes in a vertex. So currently our vertex consists of a single attribute, which is a position, and that attribute is basically 2 floats. It's a vector 2 of floats. So this is the first attribute that we have, and we currently have no other attributes. We can add other attributes like vertex normals, or we can add other attributes like color and different sort of things to each vertex, and we'll learn how to do those of course in the future videos. But for now we want to specify to OpenGL that we have a single position in this, and of course if we have any other attributes, we need to specify those as well. So the way we do that is by using a VAO, or a vertex array object. So we'll create a vertex array object, and we'll tell OpenGL what sort of attributes the vertex array has. So this is essentially like a vertex array. This is called this is of course raw data, but the thing that we render is called a vertex array, an array of vertices. And we'll tell OpenGL how to interpret that data and what to pass to our shader, and then depending on how we set it there, we'll need to get the same values in the shader. We'll of course do that in the next video, and how to use those to draw to set the color and set the position, etc. So yeah, this is currently the vertex data, and the first thing we need to do is actually upload this to the GPU. Currently it's at the CPU. We need to give that data to the GPU, and for that we need to use a buffer. A buffer, as I said, is basically an area of memory that we can store things in. And when we say a buffer in an OpenGL context, we usually mean a buffer on the GPU, which means a buffer in the GPU's memory that the GPU can access. So to do that, we'll start by and defining a GLU int. Now in OpenGL, all sorts of objects are defined using this type called GLU int, which is an unsigned integer, but it's better to use OpenGL types when you are dealing with OpenGL variables. And GLU int is basically like an ID, and every object basically that we create, it will get an ID. So we are going to start by creating a VBO. Now what a VBO means, it's basically a vertex buffer object, which means it's the buffer where we put our vertex data. And we need to create a vertex buffer, and we need to assign the ID to this VBO variable so that we can use it later, and then we need to upload our vertex data in there. So to do that, we are going to use the GL create buffers function. This function can create one or more than one buffers, and in OpenGL we also have the GL gen buffers or the generate buffers function, and these two are actually a bit different. So GL gen buffers just returns a valid ID for the buffer. So VBO will be a valid ID after we call that function. However, no buffer will actually be created, and the buffer will be created when we bind that buffer. Now this binding model is somewhat old. It's used in OpenGL 3.3 and older versions, and also later versions, but OpenGL, modern OpenGL 4.4, 4.5, 4.6, here we have direct state access, which means that we don't need to bind different buffers to do different operations on them, or any other, or most other resources. We still need to bind textures, but for most resources we don't need to bind them. So a shift away from the state machine model, you could say. And GL create buffers is a part of direct state access, and this actually creates the buffer as well instead of waiting for the time we bind it, because we are not going to bind this buffer. So here in GL create buffers we can specify the number of buffers we want, just one. Then we can give it a pointer to that, so we are going to give it a pointer to our VBO buffer, and this will create the buffer for us. Now of course we actually want to upload the data to this buffer that we have created. To do that, we are going to use the function GL named buffer storage, and the reason it's called named buffer is because if you use GL buffer storage, that operates on the binding model, so it will not actually take a buffer, it will take a binding target, and we need to bind our buffer to that target, and etc. And we don't want to use that, so we are going to use GL named buffer storage, which allows direct state access, and it allows us to basically upload data to the buffer directly without having to do any binding or anything. So the first argument it takes is the actual buffer, which is our VBO. It's the ID of the buffer, and the next argument is the size. For that we can just say size of vertex data, and then we have got the actual data. We can just pass our vertex data directly here, and then we have got some flags. We currently do not want any special things or anything, so we can pass 0 in the flags. So what this does is that it creates the buffer and it uploads this vertex data into the buffer, and now we have got the data on the GPU storage. And of course, if this is currently an array, but if you had this, for example, dynamically allocated, you could free it after that, because now the data has been copied and you don't no longer need this data on the CPU side. Well, of course this is an array, so we are going to just not do anything. Alright, so with that we have got our VBO or vertex buffer object created. Now we can create the vertex array object, where we specify to OpenGL how to interpret the data in the vertex buffer. So the vertex buffer just consists of raw storage. OpenGL has no idea what it means, and that's what we use the VAO or the vertex array object to specify. So similarly to the above one, we'll use GL create vertex arrays, and we'll use this to specify basically one and pass the pointer, and this will create the vertex array object. And now we need to specify the attributes of this and other things, but first of all we need to bind the basically we need to tell OpenGL that this vertex array will use this buffer, this VBO buffer that we have created, and it will use this one. So to do that we need to use GL vertex array vertex buffer. and this function will basically allow us to it will allow us to pass a VAO, the actual vertex array, and it will allow us to bind, for example, a vertex buffer object to it, and this will be related. So when we draw the VAO, OpenGL knows that it needs to take the data from that vertex buffer object. Now the next thing we have got is binding index. Now this is the index we need to bind to, and this is important if you are binding more than one buffer to the same VAO, so that you can access data from different buffers, but we are going to say 0 since we have a single one, the first binding index. And then we have got the GL unit buffer, which is the actual buffer. We are going to pass our VBO here, and after that we have got the offset of the buffer. So if we can actually make it so that the buffer is a large buffer, contains a lot of data, and then we access some parts of it, and we can do that using the offset and the size, but we don't care about that. We just want the buffer from the start, so we're going to say 0 here. And the last value is the stride. Now what is the stride? A stride is basically the amount of bytes or the size that we need to go from one vertex to the other vertex. It's basically the size of the vertex, but if there is any padding, it needs to account for that too. So if you are at the start of one vertex, it's the amount of bytes you need to go forward before you get to the start of the second vertex. Since there is no padding in our data, it's just 2 floats per vertex, so we can go ahead and say 2 multiplied by the size of float, and that is the stride for our vertex buffer. Now the next thing that we need to specify is the divisor. So for that we are going to say GL vertex array binding divisor, and the divisor in OpenGL is basically tells us the frequency at which we need to take the vertex data. It is specified once per buffer, or each buffer that we bind to the vertex array, and we can pass it our VAO here, and the binding index is going to be 0. We have only got one thing bound to this, so we bound it to the binding index 0 in this line, and then we have got the divisor, which we are going to set to 0. Now what is the divisor? If the divisor is 0, it just means that we want to use this data once per vertex. So each this data basically has like one value for each vertex. If it's 1, that means that it has one value for each set of vertices being drawn. So for each instance that we draw, basically we'll understand how instancing works in the future, but basically for each set of the vertices we want 1, and of course it's 2 then for each 2 sets and stuff like that. So currently of course we just want it's just plain vertex data, so we are going to go ahead and specify it as 0. So the next thing we need to do is we need to specify the attributes that we have. Currently of course we have one attribute, which is the position. So for that we are going to go ahead and do the GL vertex array attrib binding function. Now this binding function it basically specifies that this attribute is bound to this vertex buffer at this binding index. So for that we are going to give it the VAO of course, and then for the attrib index, this is the index of the attribute, and this is important. We will be using this in the shader as well, so we need to keep in mind. So currently we have only one, we are going to say 0, and then for the binding index, this is of course the buffer that this attribute is located on, which is our the single buffer that we have got bound. So yeah, this will specify that. And the next thing we need to do is we need to specify the format of this. So it's going to be GL vertex array attrib format, and this takes first of all of course the VAO, and then we need to specify the attrib index that we are specifying the format for, which is 0, that we just had, and then we have got the size of this format, and for the size we are going to just go ahead and say 2, because it consists of 2 elements, 2 floats. And for the actual type we are going to say GL float, since both are floats, and then this is normalized, and this mostly matters for some vectors and stuff. We don't need to care about that. We can pass GL false here, which is just a constant that evaluates to 0, and then we have got the relative offset, which we just need to put 0. We don't have any offsets here. If we had, for example, multiple attributes, we will need to specify how many bytes from the vertex this attribute starts from. We just have 1, so we are going to say 0. And next we just need to go ahead and say GL enable vertex array attrib, and this will enable the attribute, which means that it's actually usable. So for that we need to specify our vertex array and the index, which is just 0. And yeah, just like that we have got our vertex array object created, we have got our vertex buffer object created, and we have got our we have specified to OpenGL how this vertex array object is supposed to be interpreted. Anyways guys, this is going to be pretty much it for this video. I'll see you in the next one, in which we'll see how the shaders work and how to actually use shaders and the OpenGL pipeline to draw this vertex data that we have created in this video. So stay tuned for that. Make sure to like and subscribe and share this video with other people as well, and I'll see you in the next one, and bye.